Boosting is a cornerstone of machine learning theory, but it has a hard ceiling. For decades, we've known that generic boosting algorithms require at least omega, log 1/epsilon/gamma 2, calls to a weak learner to reach accuracy 1 epsilon. This lower bound, proven by Freund, was considered unbreakable for distribution-free learning. But what if we don't learn generic concept classes? A new paper from Stanford researchers shows we can bypass this lower bound entirely by restricting the target class to be closed under a mild XOR operation. By reframing boosting as a list decoding problem, they cut the round complexity down to just log 1/epsilon calls. Here's the mechanism. Instead of reweighting distributions like A to boost, you encode the unknown target function using a list decodable code, specifically a k-XOR code where k scales logarithmically with 1/gamma. You feed this encoded function to the weak learner. The weak learner returns a hypothesis that's slightly better than random on the encoded space, which translates to a corrupted code word. You then run a distributional list decoder on that corrupted code word. This outputs a small list of candidate hypotheses, guaranteed to contain at least one strong learner. A modest batch of additional labeled samples is used to filter the list and pick the winner. The trade-off is elegant. You save massive round complexity, but each call to the weak learner now operates on a higher dimensional space, functions over xk instead of x. If the weak learner runs in polynomial time, this only adds a polylog, 1/gamma, overhead per call. The closure assumption is surprisingly mild. For standard weak learning regimes, you only need closure under O, log n XOR, which naturally holds for DNFs, CNFs, and constant depth circuits. They also derive a distribution-specific variant that needs just a single call to the weak learner. This work bridges computational learning theory and coding theory in a way that actually changes how we think about sample versus round efficiency. If you're working on boosting, agnostic learning, or distribution-specific algorithms, the full technical breakdown is worth your time. Link to the paper in the description.